Says for, well, what we'll see is that each of the homework pools is pretty narrow this week, meaning they may only have one question in them. And so just so I'm not literally doing your homework for you, I have changed the questions to related questions. But I am going to work through all of them, and then you'll have to adapt your answer based on what I'm doing. It says for nitrogen trifluoride, draw the best Lewis structure, show all electrons and bonds with the lowest formal charge, show all non-zero formal charges, then answer the following questions. What is the hybridization on the central atom, etc., etc. And I will just tell you that on your exam, and you've seen this on last week's homework, that the question will be something like, so for some molecule, draw the best Lewis structure, and then answer the question in a multiple choice format. What is the electron geometry, or what is the hybridization on the central atom? And then you'll have a series of choices. So this is sort of good practice to do all of these together. So first thing we'll do is for NF3, we will draw the best Lewis structure. Our process, which always works, by the way, is count up the number of valence electrons, which is 5 for nitrogen, 7 for fluorine, and then there are 3 fluorines. So that's going to be 21 plus 5, which is 26 electrons. There is no charge on this species, so there are no adjustments to the number of electrons or valence electrons, which is what they really are. Then put the least electronegative atom in the center. Draw single bonds to the other atoms. And then sprinkle the valence electrons around outside atoms first. So, and I usually count them, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 24, and I still have 2 more electrons. All of my outside atoms have an octet. So go ahead and put the last 2 electrons on nitrogen. And nitrogen is an atom where many times, though not all times, we see nitrogen with 3 bonds and a pair of electrons on it. Now, if we were to do a formal charge analysis on this, we would see that all of the atoms in nitrogen trifluoride have 0 formal charge. If you'd like me to do a formal charge analysis on this, please let me know. Otherwise, I'm just going to state that because that is correct. But I'm happy to stop and do it. And if I don't hear anything, then we're going to start answering these questions. Question 1, what is the hybridization on the central atom? Well, hybridization, electron geometry, and approximate bond angles are all based on the number of electron groups around the central atom. The central atom here, nitrogen, has 1, 2, 3, 4 electron groups. And for 4 electron groups, the hybridization will always be sp3. So I guess I'll put a 1 there then. The electron geometry will always be tetrahedral. And for the approximate bond angle, there are some choices here. So for nitrogen, if there was 4 atoms around it for the 4 electron groups, then it would be a perfect 109.5 degrees. We see 1 or more pairs of electrons on the central atom. That means the bond angle will be less than 109.5 degrees. So the 2 choices really for 4 electron groups are just 109.5 or less than 109.5. Okay? And because of the electron pair, we now have less than 109.5. For and you'll see we are going to hit this pretty hard on your 3rd exam, so be aware. Now, All of these questions, actually. That's the nice thing about having made up the third exam, at least in rough draft form right now, is that I can tell you that there's these questions, you're going to get multiple versions of them.
Also, I have a question.
Yeah, go ahead, Monique.
Yeah, how do you know it's less than 109.5 degrees?
Oh, yeah, good question. So once you know there are 4 electron groups, um, the bond angle, let's see, I'm going to do my work down here. So it's always, there are 2 choices. And for the central atom with 4, let's see, 4 separate bonds, right? Then it would be a perfect 109.5 degrees. So for example, if it was CH4, those are my 4 separate bonds for my 4 separate electron groups. But now if the central atom, and these are ditto marks, with at least 1 pair of electrons, could be 1 pair, could be 2 pairs, 1 pair of electrons on the central atom. Oop, I think that's redundant, but, well, better redundant than not enough. It will be less than 109.5 degrees. So,
Okay.
yeah. And another prime example of that would be water, H2O. Water has 2 pairs, and your answer for this would be less than 109.5 as well. While for here, CH4 would be a perfect 109.5. Cool. Any other questions so far? All right. Then let's do number of sigma bonds. So sigma bonds, well, let's just review that. And I'm sort of running out of space, so I'm going to write these up here. So a single bond equals sigma bond. A double bond is a sigma plus a pi, and a triple bond equals sigma plus pi, or plus 2 pi, however you do it. So when I look at the bonds here, I have a single bond, so it's sigma, sigma, sigma. So number 4 will be 3 sigma bonds. And number 5 will be 0 pi bonds. Now question 6 says, is the molecule polar or nonpolar? And for this, I like to draw, so first off, it's polar, but I'm going to draw the shape of this and then discuss why it's polar, because another question you will likely be asked on your third exam and the final, now that I think about it, well, definitely the third exam, is going to be to draw dipoles. And I didn't specifically ask this here, but I'm going to do it anyway. So with nitrogen as the central atom, drawing the shape, there's going to be 4 tetrahedral positions. One of them is going to be straight up, and I'm putting the pair of electrons there. Another will be off to the side. And then tetrahedral shape uses what are called out and back wedges. And an out wedge is supposed to be coming out of the page at you. There we go. And a back wedge is supposed to be going back into the page. And this is nitrogen trifluoride drawn according to its shape, when its shape is tetrahedral. Now, when I draw dipoles, your dipoles will always face, your arrows will always point toward the more electronegative atom. And the more electronegative atom is closer to the top and right of the periodic table, fluorine being the most electronegative atom there is. And so my arrows will all face my fluorines. And this is really good, actually, that we've already talked about, or you've already done the lecture outline for lecture outline 11 and intermolecular forces. So these three arrows are all pointing, are all pointing in some ways down. And so the only way they could cancel would be is if there's an F here pointing up as well, but there is not. These dipoles do not cancel. Which means it's a polar molecule. And so is it polar or nonpolar? It is a polar molecule. Any questions about that? And let me see, I think I've now got the entire answer on screen.
Professor, is there any dipole on the two electron pairs?
Una, good question. Is there any dipole on the electron pair? There is not. So, and that's so whenever there's a bond, you can draw a dipole for the bonds. Of course, you would not draw a dipole if the bond was the same two atoms. But other than that, any bond can have a dipole arrow. And the thing about the electron pair is that there is no dipole. We would never draw an arrow there. That's part of what we're learning. And then the electron pair being here means that the other dipoles can't possibly cancel. So in many ways, a shortcut for doing polar versus nonpolar is if there's a pair of electrons on the central atom, it is almost always polar because the rest of the dipoles can't cancel. Hopefully that answers your question, Una. Any other questions? And if not, please ask again. But so dipole or electron pairs do not have dipole arrows.